This conference will now be recorded.
So, very good evening. Today we'll be learning about geostationary satellite and its uses and various aspects of that, and we'll take up few numerical example. So, in the last class, we had learned about satellite somewhat. Today, we'll discuss a little more, like few parameters about satellite, and then we'll go to the geostationary satellite. So, we have seen satellite means uh, so satellites are actually revolving around the earth. Okay, so like one natural satellite for earth is the moon. Okay, and see, as you see in this figure, the satellite, suppose this is some artificial satellite which is revolving around the earth. This is earth we had considered in this chapter as a solid sphere of radius r, and it has center over here, and the satellite is h distance above or h height above the earth's surface. Now what we'll do, we'll find out time period for a satellite, Sa- time period of a satellite. We had already learned how to calculate orbital speed of a satellite, so that we had done in the last class, and we had found that the orbital velocity is given by under root gm by r plus h. So this is what we have already learned. Now see, what is time period of revolution? That means the time it takes to have a complete rotation around the earth's surface, and it is to be noted that we have taken the circular orbit for our calculation sake. So look here, what is the time period for this satellite then? The time period will be given by 2 pi r plus h divided by orbital velocity, and we have already calculated orbital velocity in the previous class. We can just write this down over here. Okay, look, if we do a little bit of simplification, this particular equation can be written in many ways, so that we will see now. So look here, the same equation can be written here. Look, I'll write here itself 2 pi. See, if I bring this portion inside the square root, then it will give you r plus h whole square, and this r plus h will come in the numerator, so it will be this one, r plus h whole cube divided by gm, and here 2 pi is there. Now look, if the density of the earth is rho, then this capital M can be written as 4 by 3 pi r cube and rho. So if we put this M in this particular equation, look how the time period expression for the time period changes. R plus h whole cube divided by g m as so this m, in place of this m we are writing 4 by 3 pi. These are all happening inside the square root. Look, this also if we keep inside the root over square root, then so this will give you 4. This is pi square, so 4 pi will be cancelled. You will get 3 pi in the numerator, and then see this is r plus h whole cube divided by g r cube and rho. Now if suppose this satellite is very close to, it is very close to the earth surface, if so we have got the expression for the time period as, okay, so we had the master equation was this r plus h whole cube divided by gm. Now look, see gm, for gm what we know, gm we know it will be equal to this is near to earth surface, near to earth surface. We can write this capital G into capital M as small g r square. This we have already proved in the previous classes. So this can be written then 2 pi root over r plus h whole cube, and this gm can be written as g r square. Okay, so this is also another equation for time period. Okay, now if the satellite revolves near to the earth surface, near to the earth surface, then h can be written as 0. So if this is the case, then what will be the time period? So this is actually, this is, I'll let you know, this is very similar to, so you just keep this r square here, this is r cube, so maybe we can write this equation itself for here. So if h is 0, then this will be r cube by gm, gm, okay, or maybe if you put this m also like this here, what we have written, better we will write it here on the earth surface from here itself. Look, h is 0, so then r cube goes off, so you will get something like 3 pi by g into rho. Okay, so this is on the earth surface, near earth surface. Okay, near earth surface. Near the earth surface. Okay, so look here, if we will just put it here also, if you put h is equal to 0, you look how much you get, it will be r by g. So better we'll write what we have got there. So what we have got, 3 pi by g into rho. This is on the earth surface. Okay, all right, so we have got expression for the time periods. Now, if we want to calculate the height of the satellite, calculate the height of the satellite. So I'll just briefly I'll write the time period. So let us. So I hope you have understood this. So we'll just write now that. So let me write the time period what we have got in terms of small g also. This is r plus h whole cube. In terms of small g, I am writing because as I said, g can be written as capital G into m can be written as g r square. Okay. So this is the thing. Now look, um, if we want to calculate the height of the satellite, so let us find out height of the satellite. Height of the satellite. So in this equation, look, we have the height in this expression. So if we just square it out, so square it out, squaring the above equation. Okay, what you get? 4 pi square, then h plus r whole cube divided by g r square. Okay, let me write in a same line. So this is the thing we get. So we have to find out height. So if you want to find out height, so this is the h. So what we have to do? We have to look. I'll keep this r plus h in this side and take all of them in the same side. G r square divided by 4 pi square. This is what we get. Now we have to take cubed root. Cubed root will be 4 pi square or to the power this. Okay. Now if you want to calculate h height, so this part g square g r square by 4 pi square minus of, so sorry, this is whole to the power 1/3. So this is 1/3 minus r. So this is the expression for the height of the satellite. Okay. So I'll write. See, you can see that t square g r square r is the radius of the earth. This is 4 pi square and 1/3 like cubed root of that this quantity minus r. R is the again radius of the earth. Okay, this is the height of the satellite. So this expression we will be using while calculating the height of the geostationary satellite. Okay. Now one more point we would like to learn here. So what I'll do, I'll write down what we have learned so far. So we have learned what is time period. Time period will write this expression. Let me write the general expression for that by g r square. Let me write, or it okay. Let it be there like this g r square. And using this equation, we have calculated now the height. Height what we have got? Height we have got t square g r square divided by 4 pi square whole to the power 1/3 and then r. So this is the height we have got. Now we'll see what is the angular momentum of a satellite. Angular momentum of a satellite. Okay, let me write the orbital velocity as well. So orbital velocity we have found out in the previous day, capital G m by r plus h Okay, this is the orbital velocity. So angular momentum of a satellite. Okay, so angular momentum of satellite, we have to find out what is L. L is equal to mb orbital and r plus h. So this is angular momentum mbr. R is the radius of the circular path. So in this case r plus h. So see, if we just put the value of orbital velocity also, then we get this one. Okay, now look, this guy can be taken inside the square, and as we'll keep the m also small m, so inside the square root, then we get gm small m square, and this also will be squared, so it will be, ultimately you will get final equation, you will get like this. Okay, so this is the angular momentum of a satellite. So what we have learned today, we have learned what is the time period of a satellite which is revolving around the earth at certain height age. So, and then we have learned how to calculate the height if we know the other parameters like time period, then g, r, etc. If we know, we'll be able to calculate the height of the satellite. Again, if we know the height of the satellite, if we know the radius of the earth, if we know the angular orbital velocity, so in terms of that you can find out the angular momentum of a satellite. So g capital M small m square into r plus h. Okay, this is about angular momentum of a satellite. So we have learned uh, almost all the things about satellite. Now we'll go to a geostationary satellite. Now we'll learn what is geostationary satellite. So look, geostationary satellite is a satellite. See, when a satellite, we have learned that satellite will be revolving. Suppose this is an earth, this is earth. Okay, so when a satellite is revolving around the earth, it can revolve in any arbitrary orbit like this or like this. It can orbit around the earth in any like orbit, or like their with their orbit in any plane. Okay, so satellite can revolve around any direction. They can go from east to west. Okay, west, let me write, this is north, so it will be east and this will be west. So it can go east to west direction or west to east direction, whatever they like. Okay, so see, if satellite if a satellite is made to revolve around the earth from east to west, east to west, so satellite is made to move around the earth, okay, from east to west direction. Okay, that means sense of the revolution is east to west. Oh, I'm sorry, west to east, west to east, west to east. If a satellite is constrained to revolve west to east direction, then with time period of revolution 24 hours, and at the same time, if this orbit is concentric and coplanar to the equator, equatorial plane. Then that satellite will be called a geostationary satellite. I'll tell you why it is so. Satellite is called geostationary satellite. I'll tell you why it is geostationary. So what I said, if a satellite is constant to move from east to west direction, like revolve around the earth in west to east direction, with time period of revolution to 24 hours, and if the orbit, as you see here, the orbit of the satellite is coplanar and concentric to the equatorial plane, then this particular satellite is called geostationary satellite. Why? Because it's see, the satellite is revolving in the along the same sense or same direction as the earth is rotating about its own axis. And see, earth takes 24 hours for a complete rotation around, like, about its own axis. And if the satellite is also revolving around the sun in that particular time of revolution, then this particular satellite, which has a orbit coplanar to the coplanar to the equatorial plane, that stationary will be appearing to be at rest or stationary to an observer on the Earth's surface. I'll repeat it again. What is geostationary satellite? I have a I have the definition for that. So look here, this is geostationary satellite which is revolving around the Earth. But what is the how in which direction it is rotating? It is rotating from west to east direction. West to east direction, as the sun, as the Earth itself doing. Earth is rotating about its own axis from west to east. Okay, and the time period of revolution of the geostationary satellite is same as the time period of revolution of Earth around its own axis. So that's why this particular satellite will be appearing stationary from any place of the Earth's surface. So that's why this is called stationary or geostationary satellite, and the orbit is called geostationary orbit, as you see from here. Okay, geostationary satellite, and the orbit is called geostationary orbit. And see, this kind of satellites are used in communication purpose, television, any telecommunication purpose, or yeah. So that's why these are called communication satellite. Communication satellite. Okay. Now look, the definition you can go through from go through from here. A satellite which revolves around the Earth in its equatorial plane with the same angular speed and the same direction as that of that as the Earth rotates about its own axis is called geostationary or synchronous satellite. Okay, so this is about the geostationary satellite. Now let us see how to calculate the height and what should be the height of the geostationary satellite. Okay, so geostationary satellite, height of the geostationary satellite, how to calculate? See, we have already seen in that height of the satellite can be written as by 4 pi. Okay, pi square whole to the power 1/3, and then r. So this is what we have seen from the previous derivation. So this is the height of the geostationary satellite, and look, this time period for geostationary satellite is 24 hours. Then Earth, radius of the Earth is 6,400 kilometer. G is 9.8 meter per second. So if we put all these values here, then we can estimate the height, like at what height a geostationary satellite should be revolving, like at what height it could be placed. Okay, look, if we put all these values, you know what you get. H is equal to 3600 kilometer. So this is what you will get. This is nearly equal to that factor. So this is the height you should have for that satellite to the to become a geostationary satellite. Okay. I'm sorry. I think this is 36,000. Okay. Uh, from the Earth's surface. Okay. From the Earth's surface. I think. Okay. Let us do one thing. Let us calculate this so that our doubt will be eradicated. So it will be actually 36,000 only. 36,000 kilometers. So let us put this to this G as 0098 kilometer. This we have already kilometer. This we have to put in second. This second will be like, see, 24 hours into 6, uh 24 into 60 into 60, that is hour to second. So if we multiply that, so you will get actually this T will be 8600. So if we put these values now, look what we get is this part you will be able to get 42330, and you know this part is 6400 kilometer. So these are all in kilometer. So now if you just subtract this, so you will be getting something like 35930 kilometer. Okay, from there we can write 36,000 kilometer away. So we can have this value like this. So this is the height of the geostationary satellite. Now what we'll do, we'll just see some necessary conditions I have already discussed. See, orbit has to be concentric and coplanar to the equatorial plane, as you have seen from here. So look this one. Orbit is coplanar to the equatorial plane. Okay, and concentric also. And then its sense has to be same as the Earth. Earth goes west to east, so that we will not see any relative velocity. So the relative velocity, such that the relative velocity between Earth, and geostationary satellite. Okay, I'll write in short satellite. So velocity, relative velocity will be actually 0. And period of revolution around the earth has to be 24 hours, such that we look that stationary, and it should revolve at height nearly 36,000 kilometers above the earth's surface. Okay, so these are the few points you should remember. So any of this condition alone will not be called as geostationary satellite. All these parameters have to be satisfied, then only the satellite can be called as geostationary satellite. Now everything is fine. Now let us see what is the use of a geostationary satellite. Actually, geostationary satellite, as I said, it is very useful for various reasons. One reason is that like all types of communications, like say radio, then television, then telephone, signal communication, this happens through geostationary satellite. And how it happens? Actually, geostationary satellites, they act as reflectors. Okay, and then to study the upper region of the atmosphere of the earth, suppose we have earth, so we cannot see much things at this particular height. Okay, so upper part of the region of atmosphere can be studied by this geostationary satellite. Okay, then so with this itself, this geostationary satellite itself helps us to get the various news about weather, or forecasting of weather is actually done by getting the data from the geostationary satellite itself. And finally, to study the solar radiations or cosmic radiations, this geostationary satellite helps a lot. Okay, so these are few points, like a few uses of geostationary satellite. Nowadays it is being used extensively, and in fact every country, almost every country, they have their geostationary satellite around the earth. Okay, so geostationary satellite we have learned. Now what we'll do, we'll take up few numerical problem related to this like geostationary satellites, etc. See this problem, suppose this is problem number 1. A geostationary satellite revolves around the earth at a height 6 RE from the earth's surface. Okay, so from the earth's surface it is at 6 RE distance away. Okay, a geostationary satellite. And as you know, geostationary satellites, this is Earth. That means it has time period 24 hours, right? Now, what is the time period of revolution of another satellite in hours, which is at this much distance away? See, another satellite, they are saying that another satellite is there at 2.5, at 2.5 into RE away from the center, this orbit. So I have now one geostationary satellite, another satellite here, which is revolving around the Earth in a lesser, like small radius, that is 2.5 into 10, 2.5 into RE. So look, in this case, you have to find out if a satellite, geostationary satellite rotates around the Earth, it has a time period 24 hours. Then what will be the time period for this satellite, which is R, like 2.5 into RE away from the Earth's surface? Okay. So look, I hope you have understood the problem. There is a satellite around the Earth, that is geostationary satellite. So for it, the time period of ovulation, like revolution, is given. All right. And what is given? The radius is given, R is equal to 6 RE. Okay. Now another satellite which is here at 2.5 of this Earth's radius. Okay. So this is the, so R is equal to 2.5. Okay. Anyway, so what I'll do, I'll just do the calculation. Look here. So I'll freshly draw this. This is R. This is 6 RE from the Earth surface according to the problem. And another orbit is this, which is 2.5 RE. Okay. Now for this 2.5 RE satellite, what will be the time period? Since it is geostationary, it will have time period 24. That is what we have to know. Then you can just go ahead with that. So in this case, look, we will be writing, applying Kepler's Kepler's third law. So what is that law said? What has the Lord said? T square is equal to T square is proportional to R cube. Okay, that means this is called TQ law also. So this is saying that the square of the time period is directly proportional to the cubed root of, like cubed of the radius of that uh, orbit. Okay. So now from here we can write actually T1. Suppose in the first case it is T1. So suppose T2 square by T1 square is equal to our, we can write R2 cube by R1 cube. So this R2 is this, R2 means 6 RE plus RE, and divided by this one. Obviously this is cube, and this is a whole cube. This is again 2.5 RE. Okay, these are whole cube. And look, if we just do the simplification for this problem, so T2 square by T1 square is equal to 7 RE square, a cube, sorry, and in the denominator will be, sorry, this will be along with RE plus 2.5. This will be 3.5 RE. Cube. So look this, if you simplify, you will get 2 whole cube this is whole square. Now you have to find out what is T2. T2 will be actually 16. Okay, so 8, sorry, this is 8 into 8 root over of 8 into T1. So root over of 8 means what? Root over of 8 means 2 root 2. Okay, so what is the expression we have got here? T2 is equal to root 8 into T1. And this T1 is actually, so they have asked you to find out what is the time. Okay, so yeah, I hope, let me check once again what we have done. T1 by, oh sorry, T2 by T1, it was, okay, so this will be 3.5 RE whole cube. It was the little bit wrong, and here it was 7 RE whole cube. It will be actually 1 by 8, and here there are squares. This is Kepler's law, okay? T square directly proportional to R cube. Then we take T1, T2 and then take the ratio. Okay, so that's how it will be easier to get. So T2 will be T1 into 1 over 2 root 2. Look here, in this case T1 is 24 hours, okay, into 1 by 2 root 2. Okay, so if you do this simplification to the 12, and again root 2 upon top and bottom, so it will be 2. 2 will take care this. Okay, so the time period of the another satellite in hours, which is at 2 point RE from the Earth surface away. So it will be actually the time period for that particular satellite will be 6 into root over 2. Okay, so this is what about this problem. Now let us go to the next problem. If a planet has the same mass as the Earth and it has radius of the radius one fourth of the radius of the Earth. Suppose Earth has radius r, so this particular planet will have radius r by r. This is the radius of Earth. Okay. Now what will be the escape velocity in that planet? So you have a planet has mass capital M same. So we know what is the expression for the escape velocity. We have to find out for this planet. Let us write for the for in general what we have, root 2 gm by r. Okay. Now look, this for the Earth surface, what we write for Earth surface, this gm I write as gr square, so this will be root 2 gr. But if you take from here for the given planet, will not write this first. Let us write this itself. For this is for P, the planet. So the planet has radius how much? So G is common for all of them, and m is the mass of the satellite. Sorry, the mass of the other planet is also the same as the Earth, and then Rp, it will be R by 4. 4 goes in the numerator, so this will be the expression root 2 gm by r. So this seems to be the same that this into v escape velocity on the earth surface. Okay, so this is 2 into, so this particular, see, for escape velocity for earth surface is given by root over 2 capital Gm by r. Okay, so this is the r, so we can write that. So what is that? Then this is the twice of this planet has the escape velocity twice that of the earth. So earth has this much, how much? 11.2. So this particular planet has escape velocity 11.2 electron volt, sorry, kilometer per second. This will give you 2.24. Okay, this is the value of geostationary, the escape velocity for this particular planet, which has same mass as that of Earth, but radius is 1/4 of the radius of the Earth. So I'll stop it here for today. Next day we'll prove the Kepler's law. Next day we'll prove the Kepler's law. We have already learned what are the Kepler's laws. Now today, like next day, we'll derive Kepler's law from whatever we know, like we know the orbital velocities, etc., etc. So all those knowledge we have now. Now we'll be able to understand how Kepler's laws, like 3 laws are there. One is law of orbit, law of law of time period, and law of area or areal velocity. Okay, so those things are there. We'll derive those laws from the knowledge of this universal law of gravitation. Okay, so I'll stop it here for today. We'll meet again on Thursday, Tuesday in the next week. So that day we'll learn about Kepler's law again, and we'll derive the laws. Okay, so bye for today.